Gravity isn't what you think it is. Sure, it keeps your feet on the ground, guides the planets around the sun, and makes apples fall from trees. But here's a fact. Gravity, as Newton described it, works perfectly for everyday life, but it completely fails when we shrink down to the quantum scale. What if I told you that Newton's apple and even Einstein's space-time curvature are just the tip of the iceberg? Beneath them lies a quantum world so bizarre it defies everything we know about reality. Imagine particles that flicker in and out of existence, forces that behave like ripples in invisible fields, and a universe where gravity might not even exist as we think of it. Here's another fact. If you try to measure gravity at the smallest scales, think atoms or particles, it doesn't behave. The same force that controls entire galaxies suddenly disappears into a chaotic quantum mess. Scientists call it quantum foam, a restless sea of energy where particles pop in and out of existence in the blink of an eye. And in this bizarre environment, gravity isn't a gentle pull or a bend in space-time. It's something much stranger, something we don't fully understand yet. They never told you this in school, but gravity doesn't actually pull. It's not even a force in the way we're taught. Instead, gravity might be an illusion, an emergent property of deeper quantum interactions. Think of it like a hologram. What we see is just the surface, a projection of something more complex happening underneath. Still with me? Because we're about to dive deeper into a world where black holes might not be dead ends, where the universe itself could be a quantum fluctuation, and where hidden dimensions may explain why gravity works at all. This isn't just science, it's a glimpse into the true nature of reality. Forget Newton's apple or Einstein's equations. Gravity as we know it is being rewritten, and what we're discovering will change how we see the universe forever. What you think you know about gravity is about to be turned upside down. Gravity. It's something we rarely stop to question, yet it governs everything around us. It's the reason you're sitting firmly in your chair, the reason the moon orbits Earth, and the reason stars cluster together into galaxies. For centuries, we thought we had it figured out. Newton gave us the idea of gravity as a pulling force, a simple, intuitive explanation that seemed to work for most situations. Then Einstein came along and changed everything. Gravity wasn't a force at all. It was a bending of space and time itself. Einstein's theory of general relativity explained not just falling objects but also massive celestial phenomena, from black holes to the expansion of the universe. But here's the thing. Neither Newton nor Einstein got us all the way to the truth. Their ideas, brilliant as they were, only describe part of the picture. Newton's laws are like an old map of the world, great for navigating familiar terrain but useless in uncharted territory. Einstein's equations took us much further, giving us the tools to predict how the universe works on a grand scale. Yet when we zoom in close, so close that we're looking at the tiniest building blocks of reality, gravity seems to break down. At the quantum level, where particles are smaller than atoms and time itself becomes a slippery concept, gravity doesn't play by the same rules. Einstein's space-time warping becomes irrelevant in a world where particles blink in and out of existence, existing everywhere and nowhere at once. Imagine trying to measure gravity in this chaotic environment, where every law of physics you thought you understood seems to fall apart. This conflict between quantum mechanics and our understanding of gravity isn't just a theoretical problem. It's a massive hole in our understanding of the universe. On the one hand, we have quantum mechanics, the incredibly successful theory that describes the behavior of particles and forces at the smallest scales. On the other, we have general relativity, which perfectly explains how gravity works on a cosmic scale. But when we try to combine the two, everything collapses. For example, take black holes. These are regions of space where gravity is so intense that not even light can escape. According to Einstein's equations, black holes are simple objects with a singularity at their core, a point of infinite density where all our understanding of physics ceases to function. But quantum mechanics tells us the story doesn't end there. At the quantum scale, black holes are dynamic, chaotic places where space and time ripple like waves and particles interact in ways that defy logic. Or consider the universe's beginning. The Big Bang wasn't just a fireball explosion. It was the moment when everything, space, time, energy, burst forth from a singularity smaller than an atom. General relativity can describe what happened after the Big Bang, but it can't explain the singularity itself. That's where quantum mechanics takes over, revealing a universe where quantum fluctuations, random energy blips, could have triggered the birth of reality as we know it. But here's the frustrating part. We still don't know how to unify these two views. Gravity, as described by Einstein, is smooth and continuous, shaping the universe on the largest scales. But quantum mechanics describes a universe that is granular, filled with tiny, indivisible particles and quantum fields. Reconciling these two perspectives is one of the greatest challenges in modern physics. Scientists are trying to solve this puzzle by diving deeper into the quantum structure of the universe. They've proposed theories like quantum gravity and string theory to bridge the gap. Quantum gravity suggests that space and time themselves might be made of tiny, discrete units, like the pixels on your screen. These units create the fabric of reality, and gravity emerges as a byproduct of their interactions. String theory, on the other hand, imagines that everything in the universe, every particle, every force, is made of tiny, vibrating strings. In this framework, gravity isn't just a force, but a natural consequence of how these strings interact. String theory even predicts extra dimensions of space, hidden realms that could hold the answers to why gravity works the way it does. This search for answers has led scientists to explore the deepest mysteries of the cosmos. They're studying black holes, quantum fields, and even the behavior of particles at temperatures and densities that existed only moments after the Big Bang. Every discovery brings us closer to understanding the quantum structure of the universe, a reality that goes far beyond what Newton or Einstein ever imagined. So why does this matter? Because the universe we see, the stars, planets, galaxies, and even our own lives, is just the surface layer of a much deeper, much stranger reality. To understand gravity fully, we need to go beyond Newton, beyond Einstein, and into the quantum realm. There, we might not only find the true nature of gravity, but also unlock the secrets of space, time, and the universe itself. For centuries, Newton's and Einstein's ideas have shaped our understanding of gravity. Newton's vision was simple yet brilliant. Gravity was a force pulling objects together, from apples falling to the ground to planets orbiting the sun. Then came Einstein, who flipped the script. He showed us that gravity wasn't a force but the result of space and time bending around massive objects. His equations described how stars, galaxies, and even black holes behave, painting a picture of a universe governed by the warping of space-time. For the most part, these theories work. They explain why the Earth orbits the sun, why we stay grounded on our planet, and even how light bends around massive celestial objects. They've guided us through the vastness of space and helped us predict the movements of stars and planets with uncanny precision. But as brilliant as these theories are, they have a fatal flaw. When we zoom in on the smallest scales where particles like electrons and photons dominate, gravity stops making sense. The smooth, elegant curves of Einstein's spacetime unravel into a chaotic, flickering mess known as quantum foam. Here, particles pop in and out of existence, defying the predictability we take for granted. This is the quantum realm, and it's where the rules of classical physics break down completely. Take Newton's apple, for example. On the surface, it's a simple story about gravity pulling an object to Earth. But shrink that apple down to the size of an atom, and suddenly, Newton's laws no longer apply. The particles that make up the apple don't behave like tiny solid objects. They act like waves, spread out across space, existing in multiple places at once. In this realm, gravity isn't just weak, it's practically non-existent. Or worse, it behaves in ways we can't predict. Einstein's theory faces similar challenges. His equations describe gravity as the curvature of space-time, but they assume a smooth and continuous fabric. At the quantum scale, space-time isn't smooth. It's grainy, constantly shifting, and filled with tiny fluctuations. Imagine trying to measure gravity in this environment. Instead of clean, predictable curves, you get a storm of randomness, with particles and energy flickering in and out of existence. Einstein's equations simply weren't built to handle this chaos. This disconnect between the big and the small has created one of the greatest puzzles in physics. How do we reconcile gravity with quantum mechanics? On one hand, we have general relativity, which describes the universe on the largest scales: planets, stars, galaxies, and beyond. On the other hand, we have quantum mechanics, which governs the tiniest particles and their interactions. Both theories are incredibly successful in their own domains, but when they meet, like at the edge of a black hole or the beginning of the universe, they clash. Let's talk about black holes. These cosmic giants are the ultimate testing ground for gravity. According to Einstein, black holes warp space-time so severely that nothing, not even light, can escape. But at their core lies a singularity, a point of infinite density where the known laws of physics break down. At this scale, quantum effects become unavoidable. The intense gravitational pull of a black hole should stretch space-time into oblivion, but quantum mechanics says that particles in this chaotic environment behave unpredictably. To understand what's happening inside a black hole, we need a theory that unites quantum mechanics and gravity, a quantum theory of gravity. The same problem arises when we look at the early universe. Right after the Big Bang, the universe was unimaginably small and dense, with quantum particles dominating every interaction. In those first moments, gravity and quantum mechanics were inseparable, influencing each other in ways we still don't understand. How did the universe go from this chaotic quantum state to the structured cosmos we see today? Without a unified theory of gravity, we can't answer that question. One of the biggest challenges in bridging this gap is gravity's weakness. Compared to the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is astonishingly feeble. A tiny magnet can lift a paperclip against the entire gravitational pull of the Earth. At the quantum scale, where forces are measured in incredibly small units, gravity is so weak that it's almost impossible to detect. This makes it incredibly difficult to study gravity's quantum behavior in a lab. Another issue is the nature of particles themselves. In quantum mechanics, particles are not solid objects. They're disturbances in invisible fields that fill the universe. For example, electrons are ripples in the electron field, while photons are ripples in the electromagnetic field. These fields interact to create the forces and particles we observe. But gravity doesn't fit neatly into this framework. We don't have a quantum field for gravity, at least not one we've discovered. Some theories suggest the existence of a particle called the graviton, a quantum carrier of gravity, but we've never observed one. String theory offers one possible solution. Instead of viewing particles as point-like objects, string theory proposes that they are tiny vibrating strings. These strings vibrate at different frequencies, creating different particles. In this framework, gravity isn't just a force, it's a natural outcome of the string's vibrations. String theory also predicts the existence of extra dimensions, hidden layers of reality that could explain why gravity behaves the way it does. But string theory remains unproven, and its mathematical complexity makes it difficult to test experimentally. Another approach is loop quantum gravity, which attempts to quantize spacetime itself. Instead of viewing spacetime as a smooth fabric, this theory envisions it as a network of discrete loops. At the smallest scales, spacetime would be made up of tiny, interconnected units, like pixels on a screen. This could help explain why gravity behaves differently at quantum scales, but like string theory, loop quantum gravity is still a work in progress. The search for a quantum theory of gravity isn't just a scientific curiosity. It's essential for understanding the universe at its most fundamental level. Without it, we can't fully grasp what happens inside black holes, what occurred during the Big Bang, or how the universe works at its deepest levels. It's a puzzle that challenges everything we know about physics, pushing the boundaries of our understanding and forcing us to rethink our most basic assumptions about reality. Gravity has always been the force that holds the universe together, but as we delve deeper into its quantum structure, it's clear that we're only beginning to uncover its true nature. Newton and Einstein gave us the tools to understand the visible universe, but to unlock the secrets of the quantum realm, we need a new framework, one that unites the vast and the tiny into a single, cohesive picture of reality. Let's start with the basics. Gravity has always been a cornerstone of physics. Newton saw it as a force pulling objects together, and Einstein redefined it as the curvature of spacetime. But these explanations, while groundbreaking, only work for the big picture. planets, stars, and galaxies. When we zoom into the quantum scale, everything changes. Gravity starts behaving in ways that challenge these classical ideas. Let's break it into 6 key points to explore how this happens and how they're interconnected. 1. Newton, Einstein, and the classical view of gravity. Newton's understanding of gravity revolutionized how we see the world and the cosmos. For centuries, we viewed the universe as a vast expanse with celestial bodies following predictable mechanical paths. This model, however, was built on an assumption that gravity acted as a force, a universal pull that reached out across the universe, bringing objects toward one another. Newton's law of universal gravitation states that every mass in the universe exerts an attractive force on every other mass, and this force is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law worked well for most practical applications, allowing scientists to predict the orbits of planets and the behavior of falling objects with remarkable accuracy. But Newton's idea, while groundbreaking, was not without limitations. It viewed gravity as a force that acted instantaneously across distances, without considering how this force might affect space itself. Newton's concept of gravity, as we know, was part of the classical physics framework, where time and space were treated as separate entities and gravity was just a force transmitted through these unchanging dimensions. As brilliant as Newton's insights were, his model couldn't explain every observed phenomenon. Some questions lingered, and some behaviors seemed inexplicable under his law. One of the most puzzling mysteries was the orbit of Mercury. For years, astronomers noticed that Mercury's orbit didn't quite follow the path predicted by Newtonian physics. It seemed to shift slightly over time, a phenomenon that puzzled scientists for centuries. This discrepancy led to the work of Albert Einstein, who, in the early 20th century, revolutionized our understanding of gravity. Einstein's theory of general relativity, introduced in 1915, replaced Newton's classical view with a more sophisticated model. Rather than seeing gravity as a force acting through space, Einstein proposed that gravity was the result of massive objects curving spacetime itself. Spacetime, according to Einstein, was not a static backdrop, but a dynamic entity that could be distorted by the mass and energy of objects. A planet or a star, for instance, didn't simply exert a force on nearby objects. It warped the very fabric of spacetime around it, and this curvature caused objects to move in what appeared to be an orbit. This new perspective explained Mercury's orbit. The tiny planet's odd behavior was not due to a flaw in Newton's law, but because the curvature of spacetime around the Sun affected the planet's path in subtle ways that Newton's model couldn't account for. Einstein's theory also provided a much more accurate prediction for the bending of light around stars. According to Newton's theory, light should travel in a straight line, unaffected by gravity. However, Einstein showed that light, though massless, was still affected by gravity because it followed the curvature of spacetime. This prediction was confirmed in 1919 during a solar eclipse when astronomers observed starlight bending around the Sun, just as Einstein had suggested. The bending of light, now known as gravitational lensing, opened up new ways of studying the universe. Scientists could detect far-off galaxies and clusters of stars by observing how their light was bent as it passed through the gravitational fields of closer objects. Einstein's theory marked a dramatic departure from the classical understanding of gravity, offering an elegant explanation that accounted for previously inexplicable phenomena. Yet, as revolutionary as Einstein's general relativity was, it still rested on a crucial assumption. Spacetime was smooth and continuous. In both Newton's and Einstein's models, spacetime was considered a predictable and regular entity that could be described by mathematical equations. However, this assumption begins to break down when we delve into the quantum realm, the world of subatomic particles and the forces that govern them. At the quantum level, spacetime is not smooth. In fact, it's anything but. Quantum mechanics, the framework that describes the behavior of particles at the smallest scales, tells us that spacetime is jittery, chaotic, and fluctuating. It's not the predictable, continuous fabric that Einstein envisioned. Instead, spacetime behaves like a turbulent ocean, constantly shifting and changing. These fluctuations occur at scales far smaller than anything we can observe directly. The idea that space-time could behave in such a way was difficult to reconcile with the elegant predictions of general relativity, which assumed smooth, predictable geometry. This presents a serious problem for our understanding of gravity. The classical models, both Newton's and Einstein's, are based on the assumption of a smooth, continuous space-time. But at the quantum level, space-time becomes a chaotic, uncertain realm. This discrepancy means that when we try to apply the principles of general relativity to the smallest scales of the universe, the equations break down. The gravitational forces described by general relativity don't behave the same way in this quantum world. The idea that gravity can be understood as a smooth curvature of space-time doesn't hold when space-time itself is constantly fluctuating. For example, consider black holes. According to general relativity, the immense mass of a black hole curves space-time to such an extent that it creates a singularity, a point of infinite density where space-time becomes infinitely curved. However, when we apply quantum mechanics to this situation, the singularity seems to vanish. Instead of a point of infinite density, quantum theory suggests that space-time may become quantized, meaning that it has a discrete structure at the smallest scales. This introduces the possibility that black holes might not contain a singularity at all, but rather a quantum fluctuation at the center, where the very fabric of space-time is subject to the weirdness of quantum effects. The challenge, then, is how to reconcile these two conflicting views. On one hand, we have the smooth, curved space-time of general relativity that works well on macroscopic scales, from planetary orbits to the expansion of the universe. On the other hand, we have the unpredictable, fluctuating space-time of quantum mechanics, which governs the subatomic world. The two models, at least as currently understood, seem incompatible. This is one of the greatest unsolved problems in modern physics: how to create a theory of quantum gravity that can describe the behavior of space-time at both the cosmic and quantum scales. In the quest for a unified theory of physics, scientists have been trying for decades to merge these two perspectives. One promising approach is string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny vibrating strings. These strings could, in theory, be described within a framework that combines quantum mechanics and general relativity. However, string theory is still highly speculative and has not yet provided a concrete way to describe gravity at the quantum level. Another approach is loop quantum gravity, which seeks to quantize space-time itself, suggesting that space-time may have a discrete structure composed of tiny loops or networks of interconnected points. Though still in its early stages, loop quantum gravity offers a potential pathway toward understanding the quantum nature of gravity. Ultimately, the challenge of combining Newton's and Einstein's theories with quantum mechanics is not just a theoretical puzzle. It's a deep question about the nature of the universe itself. The classical gravity models are incredibly successful in describing the universe at large scales. Yet at the smallest scales, the universe behaves in a way that is entirely unpredictable and strange. Until scientists can find a theory that unifies these two worlds, the true nature of gravity will remain one of the most profound mysteries in physics. In conclusion, while Newton's and Einstein's contributions to our understanding of gravity have been monumental, they remain incomplete when applied to the smallest scales of the universe. Newton's model provided a powerful, simple framework for understanding gravity, but it failed to explain certain phenomena. Einstein's theory of general relativity expanded on Newton's work, providing a more accurate and nuanced view of gravity. Yet, when we enter the quantum realm, space-time becomes chaotic and unpredictable, rendering classical theories of gravity insufficient. To fully understand gravity, scientists must bridge the gap between the smooth, curved space-time of general relativity and the fluctuating, uncertain space-time of quantum mechanics. Only then can we hope to uncover the true nature of gravity and its role in the fabric of the universe. 2. Quantum mechanics, the realm of the tiny. Quantum mechanics, often described as the realm of the tiny, is a domain where the laws of classical physics, like those formulated by Einstein, no longer apply. It's a place where certainty and predictability dissolve into waves of probabilities, and particles don't behave the way we expect them to. Instead of traveling along fixed paths or existing in precise locations, particles in quantum mechanics exist as probabilities, flickering in and out of existence in what we call quantum foam. These particles are in a constant state of flux, behaving in ways that defy our everyday understanding of reality. At the heart of quantum mechanics lies uncertainty. The concept was first introduced by Werner Heisenberg in the 1920s through his famous uncertainty principle, which states that we cannot simultaneously know the exact position and momentum of a particle with absolute certainty. The more precisely we measure one of these properties, the less precisely we can know the other. This uncertainty is not just a limitation of our measurement tools, it is intrinsic to the nature of reality itself. This idea of uncertainty fundamentally challenges the smooth, predictable model of space and time that Einstein's general theory of relativity relies upon. In Einstein's view of the universe, gravity is a smooth, continuous force that operates on large scales, governing the motion of planets and the curvature of space-time. But quantum mechanics shows us that, at the smallest scales, space-time itself is anything but smooth. Instead, it is turbulent, chaotic, and constantly shifting, with particles appearing and disappearing in the quantum foam. The quantum foam is a term used to describe the chaotic nature of spacetime at the smallest scales, around the Planck length, which is approximately 1.6 by 10⁻³ meters. At these scales, the very fabric of spacetime becomes a frothy, ever-changing sea of energy and particles, fluctuating wildly. This microscopic turbulence challenges our traditional notions of space and time as smooth, continuous entities. Instead of the static, unchanging background that we take for granted in our everyday experience, the quantum foam suggests that spacetime is far more dynamic and uncertain at its core. This brings us to one of the biggest puzzles in modern physics. How can gravity, which in Einstein's theory is a smooth and continuous force, exist in this chaotic, unpredictable realm of quantum mechanics? Gravity is the force that governs the large-scale structure of the universe, shaping galaxies, stars, and planets. It is responsible for the bending of spacetime around massive objects and for the orbits of planets and moons. In Einstein's general theory of relativity, gravity is not a force that acts between objects in a direct way, as Newton originally described. Instead, gravity is the result of the curvature of spacetime caused by massive objects. The greater the mass, the greater the curvature, and the stronger the gravitational pull. In the quantum world, however, there is no such smooth curvature of spacetime. Instead, we encounter a wildly fluctuating, uncertain landscape. The notion of gravity as we understand it seems incompatible with the uncertainties of quantum mechanics. If gravity is indeed a smooth force, how can it operate in a realm where everything is in constant motion, where particles and energy fluctuate unpredictably? To answer this question, we must reconsider what gravity actually is. According to quantum mechanics, forces are mediated by particles. In the case of electromagnetism, for example, the force is carried by particles called photons. Similarly, gravity is believed to be mediated by a hypothetical particle called the graviton. The graviton, if it exists, would be a massless particle that carries the gravitational force in the quantum realm, much like the photon carries the electromagnetic force. However, despite decades of theoretical work, the graviton has not yet been detected, and its existence remains an open question. One of the primary challenges in understanding quantum gravity is the fact that gravity is an incredibly weak force compared to the other fundamental forces, such as electromagnetism or the strong nuclear force. This weakness makes it difficult to study gravity on the quantum scale, where the effects of the other forces dominate. The tiny, fluctuating nature of spacetime at the quantum level means that detecting the effects of gravitons is extraordinarily difficult, and current experiments and technologies are not sensitive enough to measure these subtle effects. At the same time, the problem of reconciling quantum mechanics with gravity is not just a technical challenge. It is also a deep conceptual problem. The idea of a smooth, continuous spacetime, as described by Einstein, is at odds with the inherently discrete, probabilistic nature of quantum mechanics. Spacetime, in the quantum view, is not a smooth continuum, but a dynamic, ever-changing fabric that can bend, twist, and flicker on incredibly small scales. This conflict between the smooth, deterministic view of gravity and the uncertain, probabilistic nature of quantum mechanics has led to the development of various theories attempting to unify the two. One of the most well-known approaches is string theory, which posits that the fundamental particles of the universe are not point-like objects but rather tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar three-dimensional space we experience. In string theory, gravity arises naturally as one of the forces mediated by these strings. The theory also suggests that at extremely small scales, space-time itself may be subject to quantum fluctuations, much like the particles that populate the quantum foam. Another approach to unifying quantum mechanics and gravity is loop quantum gravity. Unlike string theory, loop quantum gravity does not require extra dimensions or the idea of vibrating strings. Instead, it focuses on the discrete nature of spacetime itself. According to loop quantum gravity, spacetime is made up of tiny, indivisible loops that form a network, much like a woven fabric. These loops represent the smallest possible units of spacetime and provide a quantum description of gravity. In this framework, spacetime is not a smooth continuum but a discrete structure that can be quantized and subject to quantum effects. Both string theory and loop quantum gravity are still in development, and neither has been fully tested or experimentally confirmed. However, both provide intriguing insights into how gravity might behave on the quantum scale. The search for a theory of quantum gravity is one of the biggest challenges in modern physics, and it has the potential to revolutionize our understanding of the universe. Despite the challenges, scientists remain hopeful that a unified theory of quantum mechanics and gravity will eventually emerge. Such a theory would not only provide a deeper understanding of the fundamental nature of the universe, but also open up new possibilities for technologies and applications that we cannot yet imagine. It could shed light on the nature of black holes, the behavior of space-time near the Big Bang, and the true structure of the universe at the smallest scales. The search for this theory continues to drive research in both theoretical physics and experimental science, as physicists strive to uncover the deeper truths of the cosmos. As we delve further into the realm of the tiny, we are confronted with a new and unfamiliar reality. A reality where uncertainty reigns, where space-time is not a smooth fabric, but a bubbling sea of quantum foam, and where the forces that govern the universe behave in ways that challenge our intuition. Quantum mechanics forces us to rethink our understanding of the fundamental laws of nature, and opens the door to new possibilities that could change our view of the universe forever. The road to understanding quantum gravity is long and fraught with challenges, but it is also a journey that promises to reshape our view of reality. As we explore the smallest scales of the universe, we may one day uncover a theory that bridges the gap between quantum mechanics and general relativity, and in doing so, unlock the secrets of the cosmos. Until then, the tiny realm of quantum mechanics remains one of the most mysterious and fascinating frontiers in science, offering us a glimpse into a universe far stranger than we could have ever imagined. 3. Quantum fields, the building blocks of reality. In the realm of quantum mechanics, the universe is not made up of solid objects or particles in the traditional sense. Instead, it consists of invisible fields that span across space and time, and these fields are the fundamental building blocks of reality. Within these fields, the seemingly separate particles we observe in the world around us, such as photons, electrons, and even the Higgs boson, are not distinct entities, but rather disturbances or excitations in these fields. The concept of quantum fields changes the way we understand the fundamental nature of matter and energy, suggesting that what we perceive as solid, tangible matter is, at its core, a collection of complex and interacting quantum fields. In quantum mechanics, every type of particle corresponds to a specific quantum field. For instance, the electron is an excitation in the electron field, while a photon is an excitation in the electromagnetic field. These quantum fields permeate the entire universe, and the various particles we encounter are simply the result of disturbances in these fields. The beauty of quantum field theory lies in its ability to describe the behavior of particles in terms of the fields they arise from, providing a framework that ties together particles, forces, and energy in a unified manner. One of the most fascinating aspects of quantum fields is that they are not static. They are constantly fluctuating, with the potential to create and annihilate particles at every point in space. This dynamic nature is a direct consequence of the uncertainty principle in quantum mechanics, which states that there is always some inherent uncertainty in the precise state of a quantum system. These fluctuations give rise to what are known as virtual particles, short-lived particles that appear and disappear in an instant, seemingly from nowhere. Despite their fleeting existence, virtual particles have real, measurable effects on the world around us, influencing the forces between actual particles and contributing to phenomena such as the Casimir effect. Perhaps one of the most well-known quantum fields is the electromagnetic field, which is responsible for the forces we associate with electricity and magnetism. When an electron moves through the electromagnetic field, it can emit or absorb photons, which are the quanta of light. This interaction between the electron and the electromagnetic field gives rise to the phenomena of light, as well as the forces that govern the behavior of charged particles. Similarly, the weak nuclear force and the strong nuclear force are also mediated by quantum fields, with the W and Z bosons and gluons, respectively, being the particles that carry these forces. But while quantum field theory successfully describes the interactions between particles in the electromagnetic, weak, and strong forces, there is one force that remains stubbornly outside the framework of quantum mechanics: gravity. Gravity, the force that governs the motion of planets, stars, and galaxies, does not have a corresponding quantum field. This is a major gap in our understanding of the universe, as gravity is one of the four fundamental forces of nature, yet we do not have a quantum field theory to describe its behavior. The lack of a quantum field for gravity creates a profound tension between two pillars of modern physics: general relativity and quantum mechanics. General relativity, developed by Albert Einstein, provides a highly successful description of gravity as the curvature of spacetime caused by the presence of mass and energy. According to this theory, massive objects like planets and stars warp the fabric of spacetime, and this curvature is what we experience as gravity. General relativity has been confirmed by numerous experiments and observations, including the bending of light around massive objects, the precise behavior of satellites in orbit, and the detection of gravitational waves. However, general relativity does not incorporate the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. On the other hand, quantum mechanics successfully describes the behavior of particles and forces at the microscopic level. It allows us to understand phenomena such as the interactions between subatomic particles, the behavior of atoms and molecules, and the fundamental forces that govern the microscopic world. However, when we try to apply quantum mechanics to the force of gravity, we encounter a problem. Unlike the other forces, gravity cannot be described in terms of a quantum field that mediates its interactions. This creates a fundamental challenge in reconciling the two theories, as general relativity and quantum mechanics seem to operate in entirely different domains. One of the major obstacles in developing a quantum theory of gravity is that gravity is an extraordinarily weak force compared to the other fundamental forces. For instance, the electromagnetic force is about 10^36 times stronger than gravity at the atomic scale. This vast difference in strength means that the effects of gravity are incredibly difficult to detect at the quantum level, where the behavior of individual particles is governed by the laws of quantum mechanics. While we can observe the effects of gravity on macroscopic objects, such as the motion of planets or the bending of light, these effects become exceedingly difficult to measure at the scale of individual particles. Another issue arises from the fact that gravity is described in general relativity as a geometric property of spacetime. The curvature of spacetime is determined by the distribution of mass and energy, and this curvature tells objects how to move through space. In contrast, quantum mechanics is based on the idea of particles interacting with one another through quantum fields. the geometric nature of gravity makes it fundamentally different from the other forces, which are mediated by particles like photons and gluons. This difference in the way gravity is understood poses a significant challenge when trying to formulate a quantum theory that incorporates gravity. Despite these challenges, physicists have made significant progress in attempting to reconcile gravity with quantum mechanics. One of the most promising approaches is the theory of quantum gravity, which seeks to describe gravity using the principles of quantum mechanics. One potential candidate for a quantum theory of gravity is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can vibrate in different ways, giving rise to the various particles and forces we observe in the universe. In string theory, gravity is mediated by a hypothetical particle called the graviton, which is a quantum excitation of the gravitational field. If string theory is correct, it could provide a framework for understanding gravity as a quantum phenomenon. Another approach to quantum gravity is loop quantum gravity, which attempts to quantize spacetime itself. In loop quantum gravity, spacetime is not a smooth, continuous fabric, but rather is made up of discrete, quantized units. These units form a network of loops, and the interactions between these loops give rise to the force of gravity. While loop quantum gravity has not yet been fully developed, it offers an intriguing alternative to string theory and has garnered significant interest from researchers in the field of theoretical physics. While both string theory and loop quantum gravity show promise, neither has yet been able to provide a complete and experimentally verified theory of quantum gravity. The search for a theory that successfully combines general relativity and quantum mechanics remains one of the most important and challenging endeavors in modern physics. Until we can develop a fully unified theory, we are left with the tantalizing possibility that gravity could be an emergent phenomenon, a force that arises from the interactions of quantum fields rather than being a fundamental force in its own right. Emergent gravity is a concept that suggests that gravity may not be a fundamental force at all, but rather a consequence of the collective behavior of quantum fields. In this view, gravity would emerge as a large-scale effect from the interactions between quantum fields, similar to how thermodynamic properties like temperature arise from the motion of individual molecules. This idea has gained traction in recent years as researchers explore the possibility that gravity is not a fundamental force, but rather a macroscopic manifestation of more fundamental quantum phenomena. If this idea proves to be correct, it could fundamentally change our understanding of the universe and the role that gravity plays in the fabric of reality. The quest to understand gravity and its relationship to quantum mechanics is far from over. While we have made remarkable strides in understanding the nature of quantum fields and the forces that govern the microscopic world, gravity remains an enigma. The challenge of integrating gravity into the framework of quantum mechanics is one of the greatest puzzles in modern physics. Whether gravity is an emergent phenomenon or a fundamental force with its own quantum field, the answer could revolutionize our understanding of the universe and the very nature of reality itself. Until then, the search continues, and the mysteries of quantum fields and gravity remain at the forefront of scientific inquiry. For the holographic principle, gravity as an illusion. In the realm of theoretical physics, the nature of gravity has remained a subject of profound mystery. For centuries, gravity was understood as a fundamental force that governs the movement of objects, from the smallest particles to the largest galaxies. Sir Isaac Newton's laws of motion, and later Albert Einstein's theory of general relativity, provided the foundation for our understanding of how gravity works. But as scientists delved deeper into the microscopic realm of quantum mechanics, they encountered anomalies that could not be explained by the classical understanding of gravity. This led to the development of new revolutionary ideas. One of the most mind-bending of these theories is the holographic principle, which suggests that gravity, as we perceive it, might not be fundamental at all. In fact, gravity could be an illusion, a byproduct of more complex quantum processes occurring in a lower dimensional realm. At the core of the holographic principle is the radical notion that the three-dimensional reality we experience may not be as it seems. Instead of being the primary stage on which the events of the universe unfold, our 3D universe could be a projection of information stored on a two-dimensional surface. Imagine this idea like the surface of a hologram, which is a flat, two-dimensional structure that projects a three-dimensional image. In this analogy, our universe would be the image, while the real information, perhaps everything that makes our universe function, resides on a distant boundary, invisible to us. The implications of such a theory are staggering. It suggests that what we perceive as gravity, a force that governs the motion of massive bodies and dictates the structure of space-time itself, could simply be an emergent phenomenon arising from quantum information. If the holographic principle is correct, gravity might not be a fundamental force intrinsic to space-time, but rather an effect, an illusion, arising from the quantum interactions that occur on this mysterious two-dimensional surface. This theory finds its roots in the study of black holes. Black holes, those enigmatic cosmic objects with gravity so intense that not even light can escape them, have long intrigued physicists. Traditionally, it was believed that when information enters a black hole, it is lost forever, erased from the universe. However, this view is inconsistent with the principles of quantum mechanics, which assert that information must always be conserved, even in extreme conditions. This paradox, known as the black hole information paradox, posed a significant challenge to our understanding of physics. In the 1990s, the physicist Juan Maldacena made a groundbreaking suggestion that linked the black hole information paradox to the holographic principle. He proposed that information falling into a black hole could be encoded not inside the black hole itself, but rather on its surface, specifically on the event horizon, the boundary around the black hole beyond which nothing can escape. According to Maldacena's theory, the complex internal workings of a black hole could be described by a simpler, lower-dimensional surface. In this framework, all the information that seems to vanish inside a black hole is actually stored on the event horizon, a surface with just two dimensions. This insight led to the development of the concept known as ESCFT duality, or the anti-de Sitter space conformal field theory correspondence. This duality suggests that a higher dimensional space, such as the interior of a black hole, can be fully described by a lower dimensional space, such as the two-dimensional event horizon. Essentially, it was a mathematical breakthrough that suggested that the fabric of our three-dimensional universe might be nothing more than a projection from a two-dimensional reality. The holographic principle proposes that the entire universe might function in a similar way. If the information that describes the universe is encoded on a two-dimensional boundary, then the universe we experience in 3 dimensions is simply a projection of that information. This is analogous to how a 3D image of a hologram is encoded on a 2D surface. The image we see is not the real hologram, it is merely a projection, a shadow of something more fundamental. Likewise, our universe, with its vast galaxies, stars, and gravitational forces, might be a projection of quantum information stored on a distant boundary. One of the most startling consequences of this idea is its potential to revolutionize our understanding of gravity. According to the holographic principle, gravity might not be a fundamental force that exists independently in the fabric of space-time. Instead, gravity could be an emergent property, a feature that arises when quantum information is projected into 3 dimensions. It might be the result of deeper quantum processes that occur on the lower dimensional surface, processes that we cannot directly observe or measure. Gravity, in this framework, would not be a force that acts on objects in a traditional sense, but rather a consequence of the way quantum information interacts across dimensions. The holographic principle also ties into some of the most profound puzzles in modern physics, such as the nature of space-time and the unification of quantum mechanics and general relativity. General relativity, which describes the force of gravity, works exceptionally well on large scales, such as those of planets, stars, and galaxies. However, it breaks down at the quantum level, where the rules governing particles and forces seem completely different. On the other hand, quantum mechanics has been extraordinarily successful in explaining the behavior of subatomic particles, but it has no mechanism for incorporating gravity. The holographic principle could provide a bridge between these two seemingly incompatible realms. By suggesting that gravity is an emergent phenomenon, it hints that the fundamental laws of the universe may be simpler than we currently understand. The holographic principle also offers a potential resolution to the black hole information paradox. In this view, when information enters a black hole, it is not destroyed, but rather encoded on the event horizon. The information is preserved in a way that respects the laws of quantum mechanics. The loss of information, once thought to occur when an object crosses the event horizon, is instead a misinterpretation of what happens at the boundary. The holographic principle allows us to reframe the question of black holes and information, providing a new lens through which to view the mysteries of the cosmos. Despite its elegance, the holographic principle remains a controversial idea. The notion that our universe is a projection of lower-dimensional information challenges our most basic intuitions about reality. It raises questions about the very nature of existence, space, and time. How do we reconcile the experiences of a three-dimensional world with the idea that this world might be a mere projection? What does it mean for the future of science if gravity, the force that shapes the cosmos, is merely an illusion? These questions remain open and continue to fuel debate among physicists. One of the key challenges to the holographic principle is finding empirical evidence to support it. While the theory is compelling mathematically, it has not yet been proven in any direct experimental way. For the holographic principle to gain widespread acceptance, it must offer testable predictions that can be verified by observation. This is particularly difficult because the concept involves higher dimensions and the encoding of information on a surface that we cannot directly access. However, physicists are constantly exploring new avenues to test these ideas, from studying the behavior of black holes to investigating the nature of quantum entanglement. As we look to the future, the holographic principle may offer the key to unlocking some of the most profound mysteries of the universe. If gravity is indeed an emergent phenomenon, then it could change everything we know about the cosmos. It would mean that space-time, as we perceive it, is not the fundamental stage of reality, but a projection of deeper quantum processes. This would be a radical departure from everything we have learned so far. But it would also open up new pathways to understanding the true nature of the universe. In conclusion, the holographic principle offers a bold reimagining of gravity and the structure of the universe. It suggests that gravity, far from being a fundamental force, might be an emergent property arising from the quantum interactions occurring on a lower dimensional surface. This idea, rooted in the study of black holes, challenges our understanding of space, time, and reality itself. While it is still a hypothesis, the holographic principle holds the potential to revolutionize physics and offer a new understanding of the cosmos. Whether or not this theory proves to be true, it undoubtedly marks a fascinating step toward unraveling the mysteries of the universe. Five-string theory, unifying the forces. At the heart of modern physics lies a quest for a theory that can seamlessly explain the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These forces, though crucial to the universe's very fabric, seem disconnected at first glance. Gravity, for instance, acts on a cosmic scale, governing planets and galaxies, while the other forces operate at the atomic and subatomic levels, holding together atoms and governing the behavior of elementary particles. Despite their fundamental importance, these forces have resisted unification, and physicists have struggled for centuries to find a theory that can bring them all together. In recent decades, one of the most ambitious and promising ideas to emerge in this quest is string theory. It provides a potential path forward, offering a bold new perspective on the universe, its forces, and the particles that make up everything around us. At its core, string theory proposes that the fundamental building blocks of nature are not particles, such as electrons or quarks, but rather tiny, vibrating strings. These strings, much smaller than anything we can currently detect, vibrate at different frequencies, and the vibration of a string determines the type of particle it manifests as. This concept is a radical departure from the traditional particle view of physics, where particles like electrons and quarks were seen as point-like objects, having no internal structure or size. Instead of imagining these particles as dots, string theory asks us to envision them as tiny loops or strands, each oscillating in a particular way to give rise to different particles. For example, an electron might be seen as a string vibrating at one frequency, while a photon, the particle of light, could be a string vibrating at a different frequency. Essentially, the entire particle zoo of the Standard Model, electrons, quarks, neutrinos, and even the elusive Higgs boson, are all different vibrational states of one fundamental entity, the string. Each vibration, or mode, corresponds to a different particle, and the properties of the particles, such as their mass and charge, emerge from how the string vibrates. The mathematics behind this idea is complex, but the essence is simple. Everything in the universe is made from one basic ingredient, vibrating strings. One of the most fascinating aspects of string theory is its potential to reconcile two very different areas of physics: quantum mechanics and general relativity. Quantum mechanics governs the behavior of the very small, dealing with particles and forces at the atomic and subatomic level. General relativity, on the other hand, describes the force of gravity on large scales, such as planets, stars, and galaxies. The problem is that these two theories are fundamentally incompatible with one another. General relativity treats gravity as a curvature of spacetime caused by massive objects, while quantum mechanics treats particles as existing in a probabilistic framework. Attempts to merge these two theories into a single framework have been unsuccessful, and physicists have long been searching for a unified theory that could describe both the very large and the very small. String theory offers a potential solution by suggesting that gravity itself is mediated by a quantum particle called the graviton. The graviton is the hypothetical force carrier of gravity, just as the photon is the force carrier of electromagnetism. In string theory, the graviton arises from a particular vibrational mode of a string. This suggests that gravity is, at its core, a quantum phenomenon, just like the other forces. The introduction of the graviton into the quantum framework helps explain why gravity behaves so differently from the other forces. While electromagnetism, for example, is a very strong force on a small scale, gravity is incredibly weak in comparison, especially when considering the mass of elementary particles. String theory proposes that this weakness may be due to gravity leaking into additional, hidden dimensions. String theory also predicts the existence of extra dimensions, beyond the familiar three spatial dimensions and one time dimension that we experience daily. According to string theory, these extra dimensions are compactified, meaning they are curled up or hidden on scales so small that they are beyond our ability to detect. The existence of these extra dimensions could hold the key to understanding why gravity is so weak in comparison to the other forces. If gravity can spread out into these extra dimensions, its influence in the familiar three-dimensional space we experience could be diluted. This phenomenon is sometimes referred to as the leakage of gravity into higher dimensions. The idea of extra dimensions is not entirely new to physics. In the early 20th century, physicists considered the possibility of additional spatial dimensions in the context of unified theories. However, string theory goes further by not only suggesting their existence, but also providing a framework for understanding how they might work. The mathematics behind string theory requires the existence of at least 10 dimensions, 9 spatial dimensions and 1 time dimension, for the theory to be consistent. While we can observe the familiar 3 dimensions of space and 1 dimension of time, string theory suggests that the additional 6 dimensions are compactified, curled up so small that they are invisible to us. The precise shape and nature of these hidden dimensions remain a mystery, but one possible way they could manifest is through the concept of branes, multi-dimensional objects on which strings can be attached. Branes could be thought of as higher-dimensional analogs of membranes, and they play a crucial role in string theory's attempt to unify the forces of nature. Our universe, according to some versions of string theory, could be a 3-dimensional brane floating within a higher dimensional space. The other forces could be confined to this brane, while gravity, which is weak in our familiar dimensions, could spread out into the extra dimensions. As mind-bending as it sounds, string theory also opens up new possibilities for understanding the very nature of space-time itself. The vibrations of strings could not only explain the behavior of particles, but also the fundamental properties of space and time. For instance, the geometry of space-time may be influenced by the vibrations of strings in ways that are not yet fully understood. The theory suggests that space-time itself could have a dynamic structure, one that is constantly changing and evolving as the strings vibrate and interact. In addition to providing a potential framework for unifying the forces of nature, string theory has also led to the development of new ideas in cosmology and black hole physics. In particular, it has offered novel insights into the nature of black holes. The study of string theory has shown that black holes, which are traditionally understood through the framework of general relativity, could also be viewed as manifestations of the underlying stringy nature of the universe. By applying string theory to the study of black holes, physicists hope to better understand the mysterious properties of these objects, including the information paradox, which questions how information can be preserved when it falls into a black hole. Despite its potential, string theory has not yet been experimentally verified, and this remains one of its biggest challenges. The strings proposed by the theory are thought to be incredibly small, on the order of the Planck length, which is approximately 10⁻⁵ meters. This makes them far beyond the reach of current particle accelerators or experimental tools. As a result, many critics argue that string theory may not be a testable scientific theory in the traditional sense. Some physicists believe that the lack of direct experimental evidence makes it difficult to consider string theory a truly scientific theory. Others, however, argue that the elegance and mathematical consistency of the theory provide enough merit to continue pursuing it. In the absence of direct experimental evidence, string theory remains a theoretical framework, one that provides potential solutions to some of the deepest questions in physics. It suggests that the universe may be far more intricate and interconnected than we can currently imagine. The possibility of hidden dimensions, vibrating strings, and the unification of all the forces of nature offers a glimpse into a future where physics could be radically different from what we understand today. However, whether string theory will ultimately provide the final answer to the mystery of the universe remains to be seen. What is certain, though, is that the pursuit of this theory will continue to drive scientific discovery and push the boundaries of human knowledge. Whether or not string theory is the correct path, it has already expanded our understanding of the cosmos in profound and exciting ways. 6. Black holes and quantum gravity. Black holes are one of the most fascinating and mysterious phenomena in the universe, where the forces of gravity and quantum mechanics collide in extreme ways. These dense regions of space-time, formed from the remnants of massive stars that have collapsed under their own gravity, are characterized by an event horizon, the point of no return. Once anything crosses this boundary, whether matter, light, or even information, it is lost forever. Black holes defy our understanding of physics, particularly when we try to reconcile the laws of gravity with the principles of quantum mechanics. At the heart of every black hole is a singularity, a point in space-time where density becomes infinite and the fabric of space-time itself breaks down. This singularity is where the known laws of physics cease to function, creating an impassable void in our understanding of the universe. Classical physics, specifically Einstein's theory of general relativity, provides a detailed description of the gravitational forces around black holes, but it cannot account for the behavior of matter and energy at the singularity. This creates a paradox that has puzzled scientists for decades. Quantum mechanics, on the other hand, governs the behavior of particles on the smallest scales, from atoms to subatomic particles. In the realm of quantum mechanics, particles exist in probabilistic states, governed by wave functions that describe the likelihood of where a particle might be or what it might be doing. These principles operate at scales far removed from the enormous gravitational forces present in black holes, but many physicists believe that a unified theory of quantum gravity could help bridge this gap. Quantum gravity seeks to describe gravity according to the principles of quantum mechanics. The problem arises because gravity, as described by general relativity, operates on a much larger scale than quantum mechanics, which governs the behavior of particles at the microscopic level. These two theories have been highly successful in their respective domains, but have failed to come together in a single, comprehensive framework. The singularity at the center of a black hole is one area where this incompatibility becomes most apparent. The idea of a singularity is based on the predictions of general relativity, but it is widely believed by many scientists that the true nature of black holes must involve quantum mechanics. Quantum gravity theories suggest that the concept of a singularity may not be accurate. Instead, the collapse of matter in a black hole could lead to a quantum structure at the heart of the black hole, a structure that behaves in a way that is consistent with both gravity and quantum mechanics. One of the leading theories in quantum gravity is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, beyond the familiar 3 dimensions of space and 1 of time. String theory suggests that at very small scales, where quantum mechanics and gravity both play a role, the effects of the strings' vibrations could smooth out the singularity in a black hole and replace it with a more stable structure. Loop quantum gravity is another prominent theory in the quest for a theory of quantum gravity. Instead of relying on the concept of tiny strings, loop quantum gravity proposes that space-time itself is quantized and made up of discrete loops of quantum fields. According to this theory, the singularity inside a black hole could be replaced with a quantum bounce, where the collapse of matter is reversed at a certain point, and space-time is able to recover from the extreme forces involved. In this framework, the center of a black hole would not be a singularity, but rather a region where the normal laws of physics break down and the quantum nature of space-time takes over. Both string theory and loop quantum gravity suggest that black holes may not be the destructive forces that we once thought they were. Instead of acting as one-way gateways to an inescapable singularity, black holes could represent a unique opportunity to study the interplay between gravity and quantum mechanics. By exploring the quantum structures inside black holes, scientists hope to unlock new insights into the fundamental nature of reality itself. The study of black holes and quantum gravity could also provide crucial insights into the origins of the universe. If the Big Bang, the event that marks the birth of the universe, was a quantum fluctuation, understanding the quantum nature of black holes might offer clues about how the universe began. Some scientists hypothesize that the conditions inside black holes could mirror the conditions that existed at the beginning of time, when the universe was in an incredibly hot, dense state. If this is the case, black holes could serve as cosmic laboratories where we can probe the fundamental forces that shape the universe's early moments. In recent years, advances in observational techniques, such as the detection of gravitational waves and the imaging of black holes, have opened up new avenues for exploring these mysterious objects. The first ever image of a black hole, released in 2019 by the Event Horizon Telescope collaboration, marked a significant milestone in our understanding of black holes. This image, which showed the shadow of a black hole in the galaxy M87, provided direct evidence of their existence and their extraordinary properties. As we continue to study black holes, we may gain new insights into the role they play in the cosmos and how they fit into our broader understanding of the universe. The interaction between black holes and quantum gravity has the potential to transform our understanding of both physics and the universe itself. If the singularity at the center of a black hole is not a point of infinite density, but rather a quantum structure that reconciles gravity and quantum mechanics, it could lead to a major breakthrough in our understanding of the fundamental laws of nature. This could have profound implications for our understanding of space-time, the origin of the universe, and the very fabric of reality. In addition to these theoretical developments, the study of black holes and quantum gravity also has practical implications for other areas of physics. For example, the study of quantum gravity could provide insights into the nature of dark matter and dark energy, which together make up most of the universe's mass and energy content, but remain largely mysterious. Black holes may also hold the key to understanding the nature of time itself, as they challenge our conventional ideas about the flow of time and the relationship between time and space. As we continue to push the boundaries of our knowledge, the quest to understand black holes and quantum gravity remains one of the most exciting frontiers in modern physics. With each new discovery, we come closer to unlocking the secrets of the universe and gaining a deeper understanding of the forces that govern the cosmos. The study of black holes is not just an academic pursuit, but a journey into the very heart of reality itself, where the laws of physics as we know them break down and new mysteries await. Through this exploration, we may one day uncover a unified theory of quantum gravity that can explain the behavior of matter, energy, space, and time on both the smallest and largest scales. Ultimately, the study of black holes and quantum gravity may hold the key to some of the most profound questions in science. What is the true nature of space and time? How did the universe begin? What happens when the laws of physics break down? These questions continue to inspire scientists and philosophers alike as they push forward into the unknown. By studying the deepest mysteries of black holes, we may not only gain a better understanding of the cosmos, but also take a step closer to understanding the fundamental nature of existence itself. Each of these points builds on the previous. Newton and Einstein laid the groundwork, quantum mechanics introduced uncertainty, and quantum fields showed us a new framework for understanding particles. The holographic principle and string theory provide innovative ways to unite gravity with quantum mechanics, while black holes offer a testing ground for these ideas. Together, they form a roadmap toward understanding the quantum structure of the universe. This is where things get wild. Scientists believe gravity might not be a force or a curvature, but an emergent phenomenon, something that arises from the quantum interactions of particles and fields. Think of it like a hologram. The 3D world we experience might actually be a projection of deeper, lower-dimensional quantum processes. And then there's string theory. This radical idea replaces particles with tiny vibrating strings, each with its own frequency. In string theory, gravity isn't just a byproduct, it's woven into the fabric of the universe, created by the vibrations of these strings. This theory even predicts the existence of extra dimensions, hidden layers of reality that might hold the answers to why gravity behaves the way it does. But the real game changer? Quantum gravity theories suggest that black holes might not be the dead ends we think they are. Instead, they could be windows into the quantum structure of the universe, where space and time themselves dissolve. Some physicists even believe the universe started as a quantum fluctuation, a ripple in the void that exploded into everything we see today. Gravity is often considered a simple concept, taught to us with images of apples falling from trees and planets orbiting the sun. Yet, these basic examples only scratch the surface of what gravity truly represents. At its core, gravity is a fundamental force that shapes our very existence, influencing everything from the movement of galaxies to the behavior of subatomic particles. But when we dig deeper, we realize that gravity is far more than just the force that keeps us tethered to the Earth or governs the paths of celestial bodies. It is, in fact, one of the most profound mysteries in modern physics, a key to unlocking the very nature of reality itself. The journey to understanding gravity is one that stretches back centuries, from the early observations of ancient astronomers to the groundbreaking work of Isaac Newton in the 17th century. Newton's law of universal gravitation revolutionized our understanding of the cosmos by describing gravity as a force of attraction between two masses. This simple but powerful concept allowed us to explain everything from the fall of an apple to the orbits of planets. Newton's laws were the foundation upon which much of classical physics was built, and they provided a framework for understanding the world around us with remarkable accuracy. However, despite their success, Newton's laws were not the final answer. As scientists continued to explore the universe, they began to encounter phenomena that couldn't be explained by classical mechanics. The most famous of these puzzles came in the early 20th century, when Albert Einstein introduced his theory of general relativity. This new theory expanded upon Newton's work, but it also challenged some of our deepest intuitions about space, time, and gravity itself. Einstein's general relativity showed that gravity is not just a force between masses, but rather a warping of the fabric of space and time. This radical idea changed our understanding of the universe forever. According to general relativity, massive objects like stars and planets don't just exert a force on other objects, they bend the very space around them. This warping of space-time is what causes the orbits of planets and the bending of light around massive objects like black holes. General relativity also predicted the existence of black holes, regions of space where gravity is so strong that not even light can escape. But even though general relativity provided a more complete picture of gravity, it wasn't the final answer. As scientists continued to study the universe on both the largest and smallest scales, they encountered new mysteries that general relativity couldn't explain. For example, the strange behavior of particles at the quantum level, governed by the rules of quantum mechanics, seemed to be at odds with Einstein's theory. Quantum mechanics, which describes the behavior of subatomic particles, works on a completely different set of principles than general relativity. Where general relativity focuses on the smooth, continuous nature of space-time, quantum mechanics deals with the uncertainty and randomness of the microscopic world. The two theories seem to be fundamentally incompatible, leading scientists to search for a unified theory that could explain both the large and small scales of the universe. This search for a unified theory has led to the field of quantum gravity, a branch of theoretical physics that seeks to reconcile general relativity and quantum mechanics. Quantum gravity is one of the most exciting and challenging areas of modern science, as it holds the potential to unlock some of the deepest secrets of the universe. But it is also one of the most elusive, as the mathematics required to describe it are extraordinarily complex, and we currently lack the experimental tools to test its predictions directly. The quest to understand quantum gravity has led to a number of fascinating ideas, each of which offers a different perspective on how gravity might behave at the quantum level. One of the most prominent theories is string theory, which suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. According to string theory, gravity, like all the other fundamental forces, arises from the interactions of these strings. In this view, gravity is not a force in the traditional sense, but a manifestation of the way these strings vibrate in higher dimensional space. String theory has the potential to unify all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, into a single, elegant framework. Another promising approach to quantum gravity is loop quantum gravity, which suggests that space-time itself is made up of tiny, discrete units, much like the pixels on a digital screen. In this view, gravity arises from the interactions between these discrete units, and space-time is not a smooth, continuous fabric, but a network of interconnected loops. Loop quantum gravity offers a potential solution to the problem of singularities, regions of infinite density, such as the centers of black holes, by suggesting that space-time itself becomes quantized at extremely small scales, preventing the formation of these singularities. Both string theory and loop quantum gravity represent bold and innovative attempts to explain gravity at the quantum level, but neither has been definitively proven. In fact, one of the biggest challenges in studying quantum gravity is the lack of experimental data. Gravity is incredibly weak compared to the other fundamental forces, and the effects of quantum gravity are only noticeable at scales that are far beyond our current experimental reach. For example, the Planck scale, at which quantum gravitational effects are expected to become significant, occurs at distances on the order of 10 to the 35 meters, much smaller than anything we can currently observe. This makes it extremely difficult to test the predictions of quantum gravity using traditional methods. Despite these challenges, scientists are not giving up on the quest to understand quantum gravity. New experimental techniques, such as those involving gravitational waves, may offer new ways to probe the nature of gravity at both the cosmic and quantum scales. Gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, were first detected in 2015, providing a new tool for studying the universe. These waves, predicted by Einstein's general relativity, could offer valuable insights into the behavior of gravity in extreme conditions, such as near black holes or during the early moments of the universe. In addition to gravitational waves, advances in quantum computing and particle physics may eventually allow us to explore the mysteries of quantum gravity in ways that were once thought impossible. As our understanding of the universe deepens, new technologies and ideas may emerge that allow us to test the theories of quantum gravity and push the boundaries of human knowledge even further. But as we stand on the edge of discovery, it is important to remember that the answers we seek may not be as simple as we expect. Quantum gravity is a field that forces us to question everything we think we know about space, time, and reality itself. It challenges our deepest intuitions and asks us to embrace a world where the rules of classical physics no longer apply. The implications of quantum gravity could be far-reaching, from shedding light on the origins of the universe to offering new insights into the nature of black holes, time travel, and even the possibility of a multiverse. The answers we find may not only reshape our understanding of the cosmos, but could also alter our fundamental conceptions of reality. In conclusion, gravity is not just a force that keeps our feet on the ground or governs the motion of planets. It is a profound and mysterious phenomenon that lies at the heart of the universe. From the early work of Newton to the revolutionary ideas of Einstein, we have made great strides in understanding gravity, but we are still far from fully grasping its true nature. The search for a unified theory of quantum gravity represents one of the greatest challenges in modern science. And the answers we uncover may have implications far beyond our current imagination. Gravity may hold the key to unlocking the deepest secrets of the universe, but to truly understand it, we must be willing to let go of our preconceived notions and embrace a reality that is stranger, more complex, and far more fascinating than we could ever have imagined. Whether quantum gravity will provide the answers we seek, or whether it will raise even bigger questions, remains to be seen. But one thing is certain: the pursuit of knowledge is a journey that will continue to push the boundaries of our understanding and change the way we see the universe. Well, here the quantum story ends. If you love our efforts to make this kind of content, give a like and hit the subscribe button. Until then, stay curious.